Hey, good evening, AP Physics students. Mr. Curson coming at you here. Talk a little fluid dynamics tonight. Talking about Bernoulli's principles. Okay, let's talk about your garden hose, right? So you got your garden hose and you put your thumb over the end of the garden hose and the water starts coming out faster, right? We've all done this before. Water comes out faster, goes a little further. This is called an equation of continuity, and basically says, hey, water can't disappear. So the flow, when a water pipe changes diameter, the flow going into the pipe has to equal the flow going out of the pipe. All right, water can't be created or destroyed randomly. Well, what do we mean by the flow of water? Well, we mean the mass 1 per unit time of water flowing into a pipe has to equal mass 2 flowing out of a pipe. Okay, that probably seems reasonable. Now, we know that mass is pressure, density times volume. And we know that over here as well. So the amount of, and if you're dealing with water, which is an incompressible fluid, really the density is not going to change. So in some given amount of time, if I've got water flowing in a pipe here, the volume that flows in here will have to be the volume that flows out there. Well, how could I calculate this volume? Well, if this water in this area of the pipe is moving at speed v1, over here v2 would have to be faster as this area gets smaller. So again, if you think about, this water might travel some distance L1 this way, but this water over here might travel some distance L2 this way. Well, this volume is really this area times this length. So I could say A1 times L1 over T is equal to A2 times L2 over T. Well, what is this length divided by this time? Well, that's the velocity of the water, okay? So A1 times V1 is equal to A2 times V2 for water flowing in a pipe of different cross-sectional areas, or the same pipe where the area goes down. And this equation here we call the equation of continuity. Basically says, hey, water can't be created or destroyed, and it can't be compressed, so the water flowing into a pipe has to equal the water flowing out. So you're going to use this equation like on problem number 35, which refers to, and there's a good diagram to help you out on that problem on page 269. Okay? All right. So let's move on here then to Bernoulli's principle. Bernoulli's principle is a great equation. It kind of combines a lot of the ideas we've been talking about in this chapter all into one idea. Bernoulli's principle states that when the velocity of a fluid is high, pressure is low, and when the velocity is low, pressure is high. Now, this is responsible for a lot of things. This is responsible for airplanes. How come airplanes fly? Well, the air going over the top of the wings goes faster than the air going over the bottom. Therefore, it's got lower pressure, and higher pressure from below the wings provides lift, so airplanes can fly. It's also responsible for, sometimes in a storm, when there's high-speed winds going across a roof, those high-speed winds actually have very low pressure, and so roofs can get lifted off of buildings in storms. Okay, well, we're going to help you out here with problem number 40 here, okay? And problem number 40 looks like this. Now you'll have to excuse my drawing here. So in problem number 40 it says we have a water main, right? Lots of big pipe full of lots of water. And there's a fire hydrant. Oh my gosh, that's a fire hydrant. Man, I do not know how I just drew that, okay? And there's a fireman with a hose here, right? And the hose wants to be able to spray water high up into the air. I think they give us a distance of 15 meters. So, and the question states, hey, if a fire person wants to be able to spray water from a fire hydrant 15 meters into the air, what is going to be the pressure down here in the water main versus up here? And this is a good application of Bernoulli's equation here. This is Bernoulli's principle, this is Bernoulli's equation. So what we're going to do is we're going to compare two spots in the flow of water here. Location 1 and location 2. Okay? Now, this equation can work. It's best to use absolute pressure here for P1 and P2. Now, we're going to assume that atmospheric pressure is the same at here and here, that this isn't so high that atmospheric pressure is the same. So really, P1 and P2 should be atmospheric pressure plus your gauge pressure, and atmospheric pressure plus your gauge pressure. But atmospheric pressure should cancel out, okay? Now let's assume that the gauge pressure up here is really 0. That is, this water isn't under high pressure up here. When it gets to the top here, it's just regular atmospheric pressure. However, down here, this water should be under a lot of pressure so that it can spray up 15 meters. Now, another assumption we can make here is really once the water gets up to the top here, that its speed, its velocity is really 0. Okay? We don't need the water to be traveling fast as it gets up 15 meters. We just need it to get up here. Likewise, if this is a water main, we can assume that the velocity here is very close to 0. Okay? Because this is a really big pipe, all right? So it's not going to be traveling fast because it's really large. So really we have, our velocities, V1 and V2 are going to cancel out. P2 is going to be 0. So this can all break down into P2 plus rho g y1 equals rho g y2, okay? Where y1 is the height down here, which we can assume is 0, and y2 is our height up here, which we can assume is 15 meters, okay? So our pressure down here in the water main would have to be rho g y2 minus rho g y1, okay? So that is going to be equal to, which is just rho g, right, times y2 minus y1. Here, rho is the density of our water. So this is going to be 1,000 kilograms per meter cubed times 9.8 times 15 minus 0, which means that the pressure in our water main here is going to be 150,000 pascals if we multiply this all out and round to the correct number of significant figures. All right, so that's a good application there of Bernoulli's equation there. All right, nice work, physics students. Here's your joke for the day. So a guy walks into a bar and walks up to the bartender and says, "Bartender, I would like 10 times the number of soft drinks as everyone in this bar is drinking. 10 times. That's what I'd like." Bartender looks at the guy and says, "That, my friend, is an order of magnitude." All right, nice work, physics students. We'll see you later.